Hello again, this is chapter 11.1 translations. I know period 5 actually did not get the notes packet, so hopefully you have a way to follow along. I will attach the PDF to the notes to the Google Classroom. Hopefully you can kind of just jot down the notes on your own notebook paper. If you have graph paper, that's even better because it's going to be really important for this chapter. Period 6, I actually gave you the notes on the last day we met, so that'll help you. So if you do need a copy of the notes, you can print them out. I know not everyone's got a printer. I know not everyone's got paper. So hopefully you guys can do the best you can. The examples are straight out of the book, and so you can always look in the book to see how to do the problems. So for 11.1, we're going to perform translations, we're going to perform compositions, and then solve a real-life problem involving compositions. A vector is a quantity that has both direction and magnitude, or size. So size is basically another word for magnitude, how big something is. It's represented in the coordinate plane by an arrow drawn from one point to another. So the diagram you see shows a vector. The initial point is the starting point, that's P. Q is the terminal or ending point. So terminal point, ending point, don't worry about these terms. This vector is named PQ. Notice that the symbol for a vector is the single arrowhead that only has the arrow going the top. I don't know how you pronounce it, but that's basically the symbol for a vector. You would read that as vector PQ. You'll learn a lot more about vectors if you get into higher levels of math. For now, the horizontal component of PQ is 5 and the vertical is 3. So notice the vector goes right 3 up. The component form combines the horizontal and vertical components. So the component form is 5, 3. So the first number refers to the change in the horizontal or x direction. The second number, 3, refers to the change in the vertical or y direction. When you see vector 5, 3, that means it's 5 to the right and 3 up. Example 1a, in the diagram, name the vector and write its component form. So this is vector jk, and so you want to count how many units it goes left to right, and then how many units it goes down to up. So to move from point J to point K, you have to go 3 units to the right and 4 units up. So the component form is 3, 4. Take a moment to do the same thing for example 1b. Name this vector and write its component form. So this is vector PQ, and to go from P to Q, you have to go 4 to the left and 5 up. So the component form is -4, 5. So component form of vector, very simple, just tells you the direction of the vector and how far it goes. That's another word for magnitude. Okay, transformations. A transformation is a function that moves or changes a figure in some way to produce a new figure called an image. Another name for the original figure is called the pre-image. So the pre-image, think pre, the before image. Image without the pre is the same as the post-image, the after image. What you do, where the figure is after you do something to it. So a transformation basically moves or changes a figure in some way. The points on the pre-image are inputs for the transformation, and the points on the image are the outputs. So the pre-image is the before, those numbers refer to the inputs. The image is the after, those numbers refer to the outputs. Now the specific type of transformation we're doing in 11.1 are called translations. A translation moves every point of a figure the same distance in the same direction. So imagine a rectangle on a sheet of paper or a triangle. All you're doing is moving it up and down, left or right. You're not rotating it, you're not spinning it, you're not reflecting it, you're not doing anything else to it except moving it. You're not changing its direction. All you're doing is moving it. So translation maps or moves the points P and Q along a vector A, B such that one of the following statements is true. So you start out with P, you end up at point P prime. So this apostrophe-like thing, that's P prime. So P is where you start and you're moving to P prime. So P is the part of the pre-image, P prime is part of the image. Now you notice when you move all the points in the same direction, the same distance, you will end up with parallel lines. So notice that PP prime is parallel to Q prime. Okay? So that's how you know that it's a translation. Basically, all the movements are in the same direction and they're all going to be parallel. So translations map lines to parallel lines and segments to parallel segments. So PQ, if you go this way, that is also going to be parallel to P prime, Q prime. So everything's going to move together, and you're going to end up with parallel segments. So if you start with a parallel segment, you're going to end up, after you move it, with a segment that's parallel to the original segment. So notice PQ is the original segment, P prime, Q prime is the image, the post movement segment, and it is parallel to the original segment. 2a, the vertices of triangle ABC are at A03, B2, 4, and C1, 0. Translate triangle ABC using the vector 5, -1. So the first thing you want to do is graph the triangle ABC. So you have 0, 3, 2, 4, and 1, 0. Now what you're going to do is use the components of the vector 5, -1 to move each vertex, so each corner of the triangle, 5 units to the right. So the first number refers to the change horizontally, x direction, 5 to the right, -1 means 1 down. So take point A, go 5 to the right and 1 down. So you notice A moves to A prime, which is at 5, 2. You'll do the same with B. B moves to B prime, so it goes 5 to the right, 1 down. So that's at 7, 3. And point C moves 5 to the right and 1 down, so that's at 6, -1. So label this image A prime, B prime, C prime. So the coordinates again are 5, 2 for A prime, B prime is 7, 3, C prime is 6, -1. So all you're doing is taking each vertex, each corner of the shape, and moving it however many units it says to move. So in this case, 5 to the right, 1 down, and you just draw all 3 vertices and move the whole triangle. So we're taking the same triangle, and now we're going to translate ABC using the vector -1, -2. So think about what direction that the movement's going to be. So here's the original triangle, the same coordinates, but now we're moving it 1 to the left and 2 down, -1, -2. So take A, B, C, move each one down 2, left 1, and you end up with A prime, B prime, C prime. Those points are at -1, 1, 1, 2, and 0, -2. So again, all you're doing with the translation is moving the entire shape a certain direction left and right, and a certain direction up and down, and you will notice that the original shape is basically pointing the same way, it's just moved. So here's a translation rule. You can express a translation rule along the vector A, B using a rule with this notation. So x basically becomes x plus A, y becomes y plus b. So A can be negative, so it might be movement to the left if it's negative A. B might be negative, which means you're going to move down. So if it's positive, it's going to move to the right or up. If it's negative, it's going to move to the left or down. So this is a shortcut way to express a translation along a vector. You take each x component and change it by A, take each y value, change it by b. 3a, write a rule for the translation of a triangle ABC to triangle A prime, B prime, C prime. Now to do the rule, all you need is to translate one single point. So we're going to start from point A to go to point A prime. Remember, A is the pre-image where you start. A prime is part of the image or the post-image where you end up. So you want to figure out how many units do I go horizontally, left to right, and how many units do I move vertically, up or down. So you'll notice to go from A to A prime, you're moving 4 units to the left, 1 unit up. So the rule is xy becomes x minus 4, comma, y plus 1. So the minus 4 means you are moving 4 to the left. The plus 1 means you are moving each point 1 up. And notice, if you do that to points B and C, you end up with the same rule. So you only have to check one point to figure out the translation rule. Now do this rule for the translation in this picture. So now again, using point A to A prime, to go from A to A prime, you notice you have to go 2 to the right and 1 down. So the rule is x comma y becomes x plus 2, meaning 2 to the right, positive direction, comma y minus 1. So plus 2 means to the right 2, minus 1 means down 1. And that's going to be true for both points B and C as well. All right, example 4a. Graph quadrilateral ABCD with the vertices that you see and its image after the translation xy becomes x plus 3, y minus 1. So I have on this image the pre-image A, B, C, and D, the original coordinates, -1, 2, -1, 5 for B, 4, 6 for C, and 4, 2 for D. And what you're going to do is graph the translated image by taking each x coordinate, adding 3, taking each y coordinate, subtracting 1. So take each point on each corner of the quadrilateral, and you're basically going to move it 3 units to the right, x plus 3, and 1 unit down, y minus 1. So here is your final image. So A becomes A prime, which is 2, 1. B becomes B prime, which is 2, 4. C becomes C prime, which is 7, 5. And D becomes D prime, which is 7, 1. All these points, you are adding 3 to the x and subtracting 1 from the y. So negative 1, 2 becomes 2, 1. And you do that for the other 3 points of the quadrilateral. Example 4b, quadrilateral ABCD, and we're going to graph the image after translation x minus 1, y plus 4, which means you're going to take each point on the quadrilateral, but you just need to use the 4 corners, and you're going to take each of the 4 corners, move it 1 to the left for x minus 1, and 4 up for y plus 4. So the end result is A becomes 0, 2, B becomes 1, 5, C becomes 3, 5, and D becomes 3, 2. So for each one, you're subtracting 1 from the original x to get the new one, and each one you're adding 4 to the original y to get the new y. So 1 comma negative 2 becomes 0, 2. All right, to add another vocabulary term, and you're going to see this a lot in Chapter 11, a rigid motion is a transformation that preserves length and angle measure. In other words, the shape just moves. And so it can move, it can rotate, which means it spins around. It can reflect, which means you basically flip it, but the size is the same. So if you were to actually overlap the shapes, they would match perfectly. The shape is not growing or shrinking. It's rigid. So imagine you're taking a triangle and all you're just doing is moving it along the graph. You can spin it, you can reflect it, you can flip it upside down, but you're not making it bigger or smaller. All angles are the same, all side lengths are also the same. So that's called a rigid motion. A transformation, again, is just doing something to a figure. A rigid motion is a specific type of transformation where you only move it or rotate it or reflect it, but you don't make it bigger or smaller. Another name for a rigid motion is called an isometry. Okay, it maps everything exactly the way it was before, just moves it or rotates it. So this is the translation postulate. A translation is a rigid motion. In other words, if you were to move a triangle or a quadrilateral, the lengths, the angle measures are the same before and after. So the pre-image is before, the image is after. Notice all 3 angles are the same. All 3 side lengths are also going to be the same for this triangle. So here is the confirmation of that. You can see the lengths map perfectly. DE is equal to D prime E prime, and so on for the other lengths. The angles, the measure of angle D is equal to the measure of angle D prime. When you translate it, all you're doing is moving it. You're not changing the size of the shape at all. Next is a composition. A composition is when 2 or more transformations are combined to form a single transformation. So the result is a composition or transformation. So you're doing 2 more things to a shape. So you might move it and then rotate it. You might reflect it and move it. We'll look at all the other types of transformations later. Today we're just looking at translations. So the composition theorem says that the composition of 2 or more rigid motions is still a rigid motion. So no matter how much you spin it, you flip it, you rotate it, you move it, it's going to have the same dimensions, the same shape before and after. The pre-image is going to be the same angle measures, same side lengths. Example 5a, graph segment RS with endpoints negative 8, 5 and negative 6, 8 and its image after the composition. So this is what you're starting with. So the first thing you're going to do is do a translation of x plus 5y minus 2. So you can take each point R and S, you're going to move it to the right 5 and you're going to move it down 2. So this is R prime, S prime. So that's the first transformation. The second transformation, remember composition is 2 or more. The second is also a translation. Now you're going to take this new image, R prime, S prime, and you're going to move it to the left 4 and down 2. So this becomes R double prime, S double prime. So take R prime, move it down 2, left 4, and you end up with R double prime at negative 7, 1, S double prime at negative 5, 4. Now you might notice that for 2 translations, you can just combine the 2 rules into 1. So notice x plus 5, x minus 4, you can just do x plus 5 minus 4. So the net difference is plus 1 because 5 minus 4 is plus 1. For the vertical direction, notice that it's y minus 2 and then y minus another 2. So ultimately, it's 4 below what it used to be. So you can combine the translations into 1 rule, but sometimes you want to see the middle image, the intermediate image. Example 5b, take segment RS, and now we're going to again do a composition of translations. So notice it's x minus 1, y minus 4, then x plus 4, y plus 5. So first you're going to take RS, move it to the left 1 for x minus 1, then move it down 4 for y minus 4. So here is r prime s prime. Then with this shape, you're going to move it to the right 4, x plus 4, and then you're going to move it up 5, y plus 5, and that brings you up to r double prime s double prime at negative 5, 6. S double prime is negative 3, 9. So notice the total difference is 3 to the right because minus 1 plus 4 for the x's is plus 3. For the y, it's up 1. Minus 4 plus 5 is a net change of plus 1. Okay, so notice that the original segment is parallel to both of the new segments. When you're translating, all you're doing is moving it. Every translation is going to be parallel to the previous translation. Finally, example 6, you're designing a favicon for a golf website. In an image editing program, you move the red rectangle 2 units to the left and 3 units down. Then you move the red rectangle 1 unit right and 1 unit up. Rewrite the composition as a single translation. So you're basically going to combine the two rules into one. So the first says to move the red rectangle 2 to the left and 3 down. Then it says to move it 1 unit to the right and 1 unit up. So what you're going to do is combine the horizontal movements and combine the vertical movements to one rule. So 2 units left and 1 unit right means x goes from x minus 2 and then plus 1, which means a net change of x minus 1. For y, you're going to first move it 3 units down, which is minus 3, and then you're going to move it 1 unit up. So y becomes y minus 3 plus 1, or y minus 2. So the rule is x comma y becomes x minus 1 comma y minus 2. So this is a lot of material for section 11.1, but the rule for translations is something that almost everybody gets. All you're doing is moving a shape vertically some units, horizontally some units, and expressing that in a new unit or as a rule. If you have any questions, feel free to jump in to the office hours or ask me over email what your questions are.